And it's worth saying again. By the way, we're recording now. You guys can read. I just said feminism is what I said. That's why they're laughing. Look, but it is true how effed up that kind of is, right? Because I was thinking about it. On the internet yesterday, there were all these people talking about this famous math book, and it's from the 70s, 1970s. This wasn't like 1890, the 70s. And of course, in the preface, which you guys never freaking read for whatever strange reason, but the preface is important, and it's this book about some important topics in math and physics. And the whole thing, you would have never guessed that the author thought a woman might want to learn this, because everything is the reader, he, him, he, like all the, I know, not to get on the pronoun tip, but the point of this is long before all that crap, but I shouldn't say crap, I apologize, but all that. The point is, it was almost like the men who wrote these textbooks never thought in a million years that a woman would read the damn thing or want to learn physics or math, right? So I said, I feel for you guys, right? I know.
I don't want to learn physics.
See, why the hell not? Why are you bringing down the women? What do you want to learn? Oh my God.
Not physics, that's for sure.
You're like that woman on the internet I read like 2 weeks ago. She's like, women shouldn't be allowed to vote. My husband's vote's the only thing that matters. I was like, what in the hell? Physics, physics is the best. How do you hate physics? It explains the world. Anyhow, you guys, I'll tell you what.
Cool.
Physics is awesome. It is the SHIP.
Yeah.
All right. Oh my God, that's recorded. Be nice. All right. What do you guys say about me when I'm not around? Holy shit. All right. I have to say ship because the last class I replaced the P with a T 3 times. 3 times I said it.
New record.
No, it ain't. Might be a new recorded record, but not a new record. I'll tell you that much. All right. No, seriously. Look, this stuff is hard. Physics is hard. This is hard. I mean, no one's pretending it isn't. And I will repeat for the 300th time. The learning science ain't about how smart you are or intelligent. Sure, that helps. Just like if you want to play soccer or football, it helps to be strong and fast. But learning science and mathematics is really about how willing are you to sacrifice your free time to learn hardship. That's what it is. That was a good play on words, hardship and hardship, right? But it is, it's time consuming to learn this stuff. That's just what it is. I ain't got no other way to tell you. You ain't waking up tomorrow like, oh, I get Power Series, because you don't. Nobody does. No one wakes up tomorrow and says, that was a hell of a dream. I now understand Power Series. So let's talk Power Series. So our goal today is to discuss Power Series. And why is that important? Because this tells us, getting ahead of myself. This tells us about Taylor series. So on the next page, we're going to remind you what these things look like. They're scary looking because you're not familiar with them. They're really not that bad. They're just letters on a piece of digital paper, but you will have hard tacks. We should put like a blood pressure. Let's see what I like to do this. One of my favorite things about this new watch I got, this iWatch, is that it tracks my blood pressure. And right now I am at a solid, let's see, 55 beats a minute, 7 minutes ago. This is good. I looked it up. My heartbeat is like expert level. I'm going to live to be 100. Believe that. 51 beats per minute if this thing's correct. That's like elite athlete resting heart rate. All right. Just kidding. All right. Here we go. So let's go to the next page. We'll switch to some blue. So Power Series look like this. So we're going to write down the scary thing centered at A. This is going to look scary. So the compact way of writing it is using this sigma notation. K goes from 0 to infinity, and it's this scary thing. C sub K, and then it's times the quantity X minus A to the power K. So what this looks like is it looks like a number, which we're calling C sub 0, plus another number, which we're calling C sub 1 times x minus a, plus a number, which we call C sub 2 times x minus a quantity squared. And then this pattern continues for eternity. Someone chatted something up. That's right. That's a good, Ethan. Minus 20 for insulting mathletes, though. No, I'm just kidding. You ever watch those? They used to put those competitions on ESPN right around the time of the spelling bee. You ever see those weird kids in the spelling bee? Boy, that's like parental abuse. These kids are like freaks of nature. Like, who wants to memorize that stuff? I guess it's enjoyable. But then they have the math competitions on. Now, those kids, whoo, we should not insult people because it's not nice. What does my mom say? If you don't have anything nice to say? Actually, she would have said, if you don't have nothing nice to say. And I'd say, poor grammar, Mom. All right, so that's centered at A. Now, let's look at, it looks scary, but if we switch it up and let's say centered at 0, which we're going to just study these ones because these ones don't look as scary because there's less symbols happening. Notice that the subscripts on these numbers match the power of the variable. So these are, if you look in the blue up top, that's the general case. You can center a power series at any number you would like. Pick your favorite number. For A, you can center a power series there. What we're telling you is the simplest case, I guess, we shouldn't necessarily say simple, but the one that looks aesthetically simple is when we center it at 0, because then the A, that extra stuff goes away. And again, this is, you can think of this as sort of a polynomial of infinite degree. Number plus number times x plus number times x squared. I mean, most of you studied this looking thing when you were in algebra class. You would call this ax squared plus bx plus c. And then there's a cubic term, etc. Now, we told you at the end of class on Friday that Taylor series are a special case of this, where we have a specific formula for these coefficients. Okay, so the big question that we need to ask, and the lawnmowers are going to help us. The big question is, for which x, or more specifically, for which values of x do these converge? If they do, we don't even know that they're going to. So what we're alluding to is it's possible that you can pick certain values for x and it will converge, and then if you choose other values for x, it'll diverge. Now, you've already seen this with, like, say, the geometric series. You know that if you have the geometric series, it only converged when that number was between -1 and 1. So how could we study this creature? What we're going to do is we're just going to attack it. We're going to look at a specific problem, and then we are going to ask when it converges and when it doesn't converge using some of our tests that we have. And then we're going to state a general scary result, and we're going to hope that the examples help illustrate why this result is true, and then we'll move on. That's what we're gonna friggin' do. Any preguntas, senoritas and senoros and senoritas? Amigas, amigos. O'Grady es loco en la cabeza. I think that means something. All right, so how can we study this? Let's just take one. Let's take a power series. And use some tools. Now, what we're going to do is it's funny, Emily, you asked a question about this whole idea or things, how we're asking questions. When we're doing this problem, this analysis we're about to do, we're literally going to be using ideas that you have learned pretty much over the last, well, I shouldn't say pretty much. I mean, we're going to be using ideas that you've learned in every math class probably since you first started taking math class. We're going to be using some ideas from calculus. We're going to be using some ideas from algebra and, of course, arithmetic. And so it's also useful that we understand some geometric ideas. So let's just dive right into it. So here we go. Let's consider this creature. How about we take k over 3 to the power k times x minus 5 to the kth power. We'll start k equals 0 to infinity. So let's write out the first few terms of this. When k is 0, we get 0. When k is 1, we get 1/3 times x minus 5. When k is 2, we get 2/9 times x minus 5 quantity squared. And then we'll just put the ellipse here. So before we do anything, we might want to ask ourselves, is there any obvious values of x where this will converge? Is there anything where you say, oh, if I replace x with this number, it converges? Anybody want to take a shot at? Yeah? Say it again, louder. 5, right. Plug 5 and everything goes away. So that's the first observation we need to make. First observation. Note, if x equals 5, the series, even though it's boring, converges. Because you're just adding up zeros. I mean, that's boring, but nonetheless, it is a statement. It's true. Now, why is even though I'm saying it's boring, it's not necessarily boring, because here's a cool fact. You should be able to convince yourself now that every power series will always converge at its center, if nowhere else. If nowhere else. So the center here is 5, and it converges there. And the reason it's always going to converge at its center is because every single term is going to be 0, except perhaps the first one. Now, in this case, the first one is 0 as well, but that's just because there was a 0 in the numerator. Now, okay, that's good. So will it converge for any other x? So what we have to do is we have to think about what would be a good tool to use here. So let's pretend for a second we're not math students. Let's pretend we're like hairstylists, or I'm a plumber, or I'm an auto mechanic. If I'm an auto mechanic and someone comes into my shop and says my check engine light's on, can you help me? The first thing, you're not gonna, you're not just gonna take the car and then just like throw it up in the air and take the wheels off, right? You're gonna try to diagnose the problem. You're gonna think about, okay, what can I do? What tools do I have at my disposal? And so as calculus students, as students of mathematics, we need to ask ourselves, okay, if we want to study the convergence of a series, what are our tools? And we spent some time, in fact, a few classes working with all these convergence tests. And we got to figure one or two of those have to be the way to go. And so we say to ourselves, what test seems applicable? Now, there is one subtlety here. In this particular series, which is different from all the ones we studied over the last few courses, is this guy has a variable in it. It has the letter x, which represents an unknown number. So, and I've alluded to this, we have to assume that the convergence is going to depend on what value we have for x. So right away, things like the integral tests seem to be not very useful. Things like the comparison test, do they seem useful? I don't know. It seems weird. How can we compare something if we don't know what x is going to be, right? So I'm not saying a comparison test wouldn't work, but it doesn't seem like the best tool to start with because we don't know what the value of x is. Now, there are two sort of sirens going off, and you're going to notice this in many power series. It's first off, by definition, power series have a power. And so right there, the power suggests, okay, maybe the root test can be of use. Now, the problem with the root test is, as if you did the homework, at least you would notice and did some practice, is that the root test is sometimes difficult to use because you're taking a limit of roots. And that's not always easy to do. Sometimes those expressions are complicated. Now, that being said, we might not have an issue with this. But even if we don't want to, even if we go ahead and use the root test, that's fine. But another test that seems to be very applicable here is also the ratio test. And the reason for that is because, and you might have noticed this theme if you've done enough practice, even though there's powers here, the nice thing about the ratio test, when you have powers that are the index, many things cancel because you're taking the kth plus 1 term and you're dividing it by the kth term. And so if you've done those problems with those series, you've recognized that lots of things disappear. So a good rule of thumb when you're studying power series is to use either the ratio or the root test. I myself prefer the ratio test if I can use it, and so that's what I'm going to do here. So does anybody have a question or comment? Okay, so let's get at it. So let's also remind you of this. This is worth noting. In Calc 2, I'm not saying in the real world, but in Calculus 2, we typically study power series using the ratio and/or the root test. So I'll use the ratio test because I like it. So here's what I need you to note. And I would encourage you to do this in the beginning when you're learning these things, because it's just, even if you're getting good at it, it's worth doing. So note, what is my C sub k? C sub k, if I go to the previous page, my coefficients were k over 3k. So this is k over 3k. Now, one of the subtleties is that is just a coefficient of my power series. But what is the whole kth term in my series? So I'm going to call that A sub k. A sub k is C sub k times x minus 5 to the power k. And so let me write that out. The kth term, which is what I'm really after, is this. So this is one of the places I see students make some mistakes. Do not confuse the general term of the series, which I'm calling A sub k, with the coefficient of the power series. They're two different things. One is a piece of the other. We get that? Maybe, maybe not. Okay, so if that's A sub k, what can we conclude then? Well, what is the kth plus 1 term? Well, that becomes k plus 1 divided by 3 to the power k plus 1. And that's times the quantity a minus 5 to the kth plus 1 power. Yikes. So this is, right now, we are writing down the terms of the series. And we want to use the ratio test, which means we have to take the kth plus 1 term and divide it by the kth term. Now, I don't need absolute values here because k is always positive. Yes or no? True, but what about x minus 5? What if I choose a number less than 5? Then that is negative. So I do need absolute values here. So we need to compute, and we'll do this on the next page. The ratio test says we need to compute the limit as k goes to infinity of the absolute value of the kth plus 1 term over the kth term. Now, here's where, if you practiced over the last week or so, you're not going to have a hard time with what I'm about to write. Because if you've practiced and you did the homework, you'll remember that these ratio tests, almost always, it looks ugly if you write it down as a ratio, but you're always dividing a fraction by a fraction, which means you're multiplying by a reciprocal. So here's what we end up happening. So the limit as k goes to infinity of the absolute value of the kth plus 1 term over the kth term. The kth plus 1 term, as we already saw, was k plus 1 over 3 to the power k plus 1. And then that's, since it's upstairs, we'll write it like this. And then that's divided by a sub k. So when we multiply, we flip. So it becomes 3 to the k over k. And then this is 1 over x minus 5 to the power k. And what's very nice about this is lots of things simplify. This and this go away. This and this go away. And what remains is the following: k plus 1 over k times x minus 5. Now there's one, yeah, there's a 3, yep, right here. Now the next thing to note is the limit is in terms of k, which means that x minus 5, as far as the limit goes, is irrelevant. So what I might think about doing is pulling that outside. So using the basic properties of absolute value, outside I have x minus 5 in absolute value. And inside the limit, I am left with nothing more than k plus 1 over 3k. And this becomes nothing more than absolute value of x minus 5 times a third. Well, right, we got to get there in a second, yeah. So all we've done is we've taken this limit, and now we have to understand what this limit means. So there's a lot happening here. Does anybody have a comment or a question on how I computed this limit? I took some liberties with algebra. You might have to fill in some pieces. I hope you do. All right, so here's what we know. We know that the series will converge if this value is less than 1, and it'll diverge if this value is greater than 1. So let's note that. Here's what the ratio test says. Ratio test says 3 things. The first thing it says is the series converges for 1/3 times the absolute value of x minus 5 less than 1. It tells us the series diverges for 1/3 times x minus 5 in absolute value greater than 1. And for the third thing, the ratios test says nothing when 1/3 times the absolute value of x minus 5 equals 1. So since the ratio test says nothing, that means we're going to have to be careful about what we can conclude. So now here's where we're in, the problem leaves the realm of calculus, and now we are in high school algebra. We are solving inequalities now. And I can just hear Mrs. Maycar right now telling me in 10th grade college algebra, you solve the inequality. And then she'd smack the wall with her stick. She always carried a stick. I wonder if she's still alive. What a great teacher she was. Old fashioned. She used to keep the points of everybody on the board so you could see. You ain't allowed to do that anymore, huh? You get fined. Snowflakes, I guess I am a snowflake, but the other really snowflakes would cry foul, and they say that's unfair, you're making fun of people. We keep scoring life though. Why can't we keep scoring school? I never understood that. All right, so what can we conclude? Well, we can solve these things, so let's do that. So note 1/3 times the quantity or absolute value of x minus 5. That is less than 1. Well, that's the same thing as the absolute value of x minus 5 being less than 3. Now, what does this mean? This means, by definition of absolute value, this means -3 less than x minus 5 less than 3. And this means that if I add 5 to everything, I get 2 less than x less than 8. So we guarantee convergence when x is between 2 and 8. As the weed whackers. So here's a cool side I'd like to look at that I don't know that many of you make the connection. Before we go to the next page, does anybody have a question about this? One of the things I found is that most of us can't make the connection of the geometric interpretation of what this algebraic stuff means. And that's unfortunate because if you think of the picture, it's a lot easier to solve this or to reason what it means. So first off, understand what absolute value does. Absolute value of x minus 5, what that's saying is that is measuring the distance on the number line between the x and the number 5. How far apart are we? That's what absolute value is doing. And so what we're really asking, what this thing says right here, this algebraic little expression, inequality, it is saying we want to know all x that are within 3 units of 5. What numbers x are less than 3 units from 5? That's what this means. And of course, if you look at a number line, it's 2 to 8. Those are all the numbers that are within 3 units of 5. So if we draw a picture, which is sometimes useful to do, let's take our number line. And if I put my center here at 5, and I go out here to 8, and I go over here to 2, the fact that what this is showing is that the distance between these two numbers is 3, and the distance between these two numbers is 3. So that's where it converges. Now, what we get for free then, for free, thus the series diverges when x is greater than 8 and x is less than 2, automatically. So the only analysis that we haven't done yet is what happens at 2 and what happens at 8, because the ratio test was useless. It didn't do anything for us. It gave us information about everybody but 2 and 8. This is so much fun. I don't even know what to do with ourselves. We're spent essentially like an hour on a problem. Isn't this fun? Power series, the way of life. We can do a dance. Check out our watch. Let's see. Oh my God, I need to move. I need to move 52.4% for my day. This is tragic. All right. Very good. All right. So the only thing that remains is to study or investigate x equals 2 and x equals 8. And we have to do that separately. And again, let me reiterate why we have to do that. We have to do that separately because those are the 2 points when this is true. And we know when it equals 1, the ratio test is useless. There's a saying that my father-in-law always says, they're useless as blood on a blood, but I can't say it out loud. Never heard that one before? No, it's because I censored it. I censored it. I'm like the news with the Trumpster. Weren't they censoring the Trumpster the last couple of days every time he talks? They say, no, they revoked the Trumpster's talk. What a time to be alive. Yeah, I have to put 2 in for x, and then I have to put the value for 8 in for x. So let's do that. So we'll do each one separately. If x is 2, what do we have? Well, the series becomes, so remember, what was the series? It was k over 3k, right? K goes from 0 to infinity. And this was x minus 5, so this becomes negative 3 to the power k. And what does that? Well, let's rewrite this, if you will. And there's a couple ways you can think about this. Negative 3 to the power k divided by 3 to the k. Well, what I would tell you to consider is that negative 3 to the k is negative 1 to the k times 3 to the k. So this thing simplifies to nothing more than negative 1 to the power k times k. And this thing equals 0, and then it's negative 1. And when k is 2, you get plus 2. When k is 3, you get minus 3. And then you get plus 4. And then minus 5, blah, blah, blah. How did I get minus 1? So again, exponent. Yeah, okay, so the question was, how did I get minus 1? So here's the way you should think about this. What you should do is note negative 3 to the power k is negative 1 to the power k times 3 to the power k. Right? So negative 3 to the power k over 3k is just negative 1 to the power k. Those exponent properties. Does that make sense? Man, it's kind of tricky. Now, this diverges, this series diverges by the divergence test. Why? Because the terms aren't going to 0, they're going to infinity. So since the limit as k goes to infinity of -1 to the k over k does not exist. The series diverges. And we have to be clear, why does it diverge? It diverges by the divergence test. I mean, we're really analyzing the heck out of this creature. All right, now, a similar thing's going to happen when we replace x with 8. When I set x equal to 8, the series becomes k divided by 3k times 3 to the power k, which simplifies. There's no minus sign now. So this simplifies to just k, which is 1 plus 2 plus 3 plus 4 plus ... This also diverges by the divergence test. So what is our conclusion overall? The conclusion is that the series we started with, k divided by 3 to the power k times x minus 5 to the k. This converges absolutely for x between 2 and 8. Diverges everywhere else.
Is there a case where if there's enough like that, right? But when you put 2, you get.
Oh yeah. So I think your question is there ever a case where it converges for one or both? Yeah, absolutely. I can give you a series where it converges at one of these endpoints and diverges at the other and vice versa. There can also be one where it converges at both endpoints. So what we did with this example is we actually illustrated a very, very powerful result. And that is power series have this inherent symmetry in it, that they are going to converge on this symmetric sort of neighborhood around their center. If they're going to converge at all. So some key ideas. There is some inherent maybe inherent is a bad way to say it. So maybe we should say natural. There is some natural symmetry in the region, or the interval, I should say, is a better word. In the interval where the series converges. And we drew that, so let's draw it again. If this is our number line, we know it converges at 5, and we also know that it converges between 2 and 5. So here it converges. Both of these distances are 3 units. And so because of this symmetry, it doesn't just happen in this problem, it happens all the time. So we call 2, 8 the interval of convergence. And then we call 3 the radius of convergence. This will always be the case unless something better happens. So it turns out that this is one of the 3 scenarios that can happen with a power series. And hence, not just with a power series, but with a Taylor series. Right? All right, so the previous example illustrates one scenario of a powerful theorem. So let's consider a power series. Consider the series K goes from 0 to infinity of C sub k times x minus a to the power k. There are 3 scenarios. So the first scenario is the series converges for all x. So I can give you, and we'll give you some of these on homework, where it's going to converge for all x. You do what we just did, and it turns out it converges for all x. The second scenario, and this is the one that we just witnessed, there is r greater than 0, such that the series converges for x minus a less than negative r and, excuse me, greater than negative r and less than r, and diverges for x less than negative r and x greater than r. So that's the scenario we just had. What was our r? We found it to be 3. So what did we call this? So r is called the radius of convergence. And then the interval a minus r comma a plus r is called the radius, or excuse me, the interval of convergence. I'm running out of space, so I'm squeezing it in there. I apologize. Notice I didn't say anything about what happens at r or negative r. I didn't say anything about that. Actually, there's a slight typo here. Let me fix this. I sort of lied. I didn't lie. I wrote down the incorrect thing. This is a typo. This should not be negative r. This should be negative r plus a or a minus r. Remember, because in our previous problem, this was the number 2. So this would be a minus r, and this would be a plus r. Now, let me explain something. Do not try memorizing this. You don't need to memorize it. This is all these conclusions come directly from applying the ratio test. You don't need to memorize this. Do not memorize it. Do not just do problems. Do problems. Okay, and the last scenario is kind of the worst of all 3, and that is the series converges only at x equals its center, x equals a. That's kind of the boring case, right? But we could definitely get, construct ones that do that. Now, it should be noted here, because I guess also I should be very clear about this. Let me be a little more clear, because I didn't state it there clear enough. So in scenario 2, it is possible that the series converges at x equals a minus r and or x equals a plus r. So these values must be checked separately and could change the interval of convergence, right? Because as you suggested, Shobit, they could be included. In our example, they weren't included, but they could be. So there's like some good news and bad news in all this. It's quite wild because we started this idea talking about Taylor series, and then we pondered the question because we looked at graphs. And we said, if we get these Taylor polynomials, the graphs seem to match. And so we started saying, wow, this looks cool. It looks like these polynomials in some way sort of this series converges to like e to the x or sine. But we really haven't answered that. All we've done here, if you think about it, is we've said that a series can converge. We ain't telling you what it converges to, right? So, you know, think of this world, this real weird scenario. It's possible that a Taylor series converges, but it doesn't converge to anything that's related to the function that we build it off of. So that's the next thing we need to investigate. And I don't know, I shouldn't say I don't know, it is very difficult at this level of your mathematical journey for you to appreciate that. It's one thing to say something converges, but it's a whole nother thing to tell you what it converges to. And so that's kind of where we have to go with this. Does anybody have a question or a concern? Fun times, huh? Here's a cool thing though. Power series seem to be like, they look like they're going to behave like polynomials. They look like polynomials, right? So we would imagine then that they should be easy to manipulate. That is, we would imagine we should be able to add them and subtract them like polynomials. We would be able to differentiate them and integrate them. And it turns out you get to do all that, provided that it converges. So here's a weird thing we're gonna talk about that's sort of the next step. And this is gonna make pretty much tie everything you've done in Calc 1 and Calc 2 together now. It's kind of like, I don't want to say unifying, but in a weird way it is. So here's an amazing fact. We can treat power series just like polynomials when restricted to their interval of convergence. So this means really, really, interesting things. That means we can, for example, if I have two power series, I'll call one C sub k. I won't center them at A. But I can add and subtract. We'll call the next one B sub k, X sub k. So I can, in a natural way, I can sort of add and subtract them. I can differentiate them. I can integrate them. You know, I'm skipping over some of the details, but we don't care about the details necessarily in calculus 2. Well, we do, but not exactly all the hypotheses. So we're going to be able to treat these like regular polynomials, and they're going to converge, and they're going to have these nice properties, and it's going to allow us to do a lot of analysis on complicated things quite easily. And we'll talk more about that on Thursday. Any questions, comments, concerns? All right, this is a good place to stop. I will be posting some assignments for you, and we will move on. All right, any questions, comments? All right, thank you guys very much.